Hello, today I'll be talking about the Lagrangian duality of regularization and how we can talk and see that it's a constraint optimization problem. Let's start with the budget analogy. Imagine you are a businessman who wants to create a product, and in this case, you want to maximize the quality of that product when shipping it, when leasing it. That is, you want to minimize the badness of the product. That's the equivalent view. Regularization would be to simultaneously control both the quality of the product, but also consider the cost of the product, how efficient it is. And in this case, you want to minimize both the badness of the product and you also want to minimize the cost of that product. But there's another view to this. Normal regularization is about maximizing product quality and minimizing costs simultaneously. But equivalently, we can see this as a hard, constrained view. This is called the constrained view of regularization, and it's where we maximize product quality, but we enforce it such that our cost must stay under a predefined budget. There's a hard cap or hard limit to it. Translating this back to machine learning, this would be saying we want to minimize the empirical risk, we want to minimize that loss, but at the same time, we want to we want to follow the rule or the constraint that our complexity must not exceed a certain cap, a certain hard uh, limit. As you can see, we're saying instead of saying and like maximize, minimize loss and minimize cost and complexity, instead of that we're saying but. So we're saying minimize the empirical risk, but also keep the complexity as lower than um, some value. Mathematically, we can compare the two forms. Original form is the regularization form. We want to minimize, we want to make the empirical risk as small as possible, as well as uh, the complexity. So we want to make both as small as possible. So we have that flexibility. It doesn't really matter how small we make it, as long as we get the general idea of making it small. Constraint optimization form, that's a bit more explicit. We're minimizing the empirical risk. Again, that's flexible, but this time we're subject to the that the uh, complexity, given that the complexity must be smaller than or equal to some uh, some budget thing. So as you can see, it's also equally flexible, except we have to keep it under some certain predefined value. Obviously, the original form would be much more viable in practice, as we often can't pin down what appropriate C would be. So we don't know how to afford the budget. Instead, we let the model learn that themselves, which gives the original form, saying make it as small as possible instead of make it below this certain number. So implicitly giving the general gist of it without having to go through all the definition issues in practice. And they also mean the same thing. So it's two sides of the same coin. That's why it's called the Lagrangian duality of regularization. The two forms, as you can see here, the original form and the constrained form, they're just two ways of saying the same thing. They're both regularization. And because they are the same thing, we can thus interpret regularization as constrained optimization, where lambda, the strength hyperparameter of the regularization, is a Lagrange multiplier controlling the strength of the constraints. Regularization is essentially saying, do this given you follow this rule, or you don't make it as the complexity that high. In summary, if we go back to this mathematical slide, regularization can be seen as constraining, a hard constraint and soft constraint form. So the soft constraint is make both as small as possible, and then the hard regularization form or the constrained optimization form, which is equivalent, that's essentially saying make the loss as small as possible, but follow the condition that this must be smaller than some budget or complexity.